So, the next talk comes from an expert on open hardware. Over more than a decade, Sean Cross, alias xobs, has created independent hardware projects on every layer of the project product stack. Today, he takes us on a journey through the world of microcontroller debugging. Enjoy the talk, Demystifying Common Microcontroller Debug Protocols.
Thank you. First, let's give a round of applause for the heralds and the angels for putting up with all this and generally keeping things moving smoothly. So thank you very much. So once again, thank you everyone for coming. And this talk is going to be about demystifying common microcontroller debug protocols. And this came about because I've used debuggers and debug hardware for the longest time, such as there on the left, and I've used GDB on the right, and I've been asking myself, what's going on in between? There's these two very different things, and there's a gulf in the middle. And my question has been, what is actually going on the wire? So first, a little bit about myself. As she mentioned, I've been working with open hardware and open software projects for basically my entire career. Started out with the Novena Open Laptop, which had a power supply in there called Senoko as the battery management unit. These actually were done in a time before we had really good open hardware tooling, so there wasn't really any kind of OpenOCD existed, but it wasn't really a point where it worked well. And then I moved on to FOMU, which was an FPGA development board. We had to make our own CPU based on the VEX RISC-V core, so we added debugging to that. And then we reused a lot of that machinery for the Be Trusted Open Communicator. I'd like to talk about what we're not going to. First, I'd like to talk about, we're going to cover 4 things in this talk, assuming we have enough time. We're going to cover the minimum viable debug, what you need in the hardware to actually be able to set up a debugger. We're going to cover JTAG. We're going to cover ARM's ADI v5 and the MEMAP. And then we're going to take a little detour and talk about some of how RISC-V does it. What we're not going to talk about is we're not going to cover the actual debug hardware. There's lots of solutions available that are both very expensive and not so expensive. Lauterbach makes some very nice tools. Sager makes J-Link, which can be either very expensive or if you're educational, it can be very cheap. All of these here are very readily available. The interesting thing is that ARM decided that there was way too many different kinds of debuggers, so they came up with called CMSys DAP, which is a USB protocol for talking with SWD devices and JTAG devices, kind of unifying them all together. And everything up here is a CMSys DAP compatible device, including that Raspberry Pi Pico probe. We're also not going to cover software. There's lots of good existing software that exists today. I mentioned OpenOCD, there's Python, PyOCD, ProbeRS, the Blackmagic debug application, and these all talk to your probe and provide a GDB server. And if you want to know what GDB is doing under the hood, you can run this command set debug remote, and then you can see the actual protocol as it is going along. So if you want to learn more, give that a shot, and you can actually learn what is going on under the hood. So with that, let's talk about the minimum viable debugger hardware. If you want to make a debugger, you basically need these 8 things. We need a way to peek and poke memory. We need a way to read and write the registers of the CPU. And we need to be able to control the CPU, that is, halt it, single step it, reset it, or add a breakpoint. So as a kind of an example, I'm going to talk about the VEX RISC-V soft core that we used for FOMU and we used for Be Trusted. So the VEX RISC-V is a CPU that's written in Scala, and it's designed to be put in FPGAs, but it's also been done in some silicon projects. It's a 32-bit RISC-V core, but the most important thing is it has plugin support, and you can see an image on there. This is the plugin for the FPU. Plugins can do a lot in this CPU, from adding custom instructions to adding entire pipelines to the CPU. But the one we're interested in is the debug plugin, which is interesting because it's only 2 registers. For starters, there's this 32-bit register here. This is address 0. And You can see in here that I've highlighted, well, basically everything in here, because from this one register, you can do things like reset the CPU. You can test to see if it's halted. If the step bit is set and you unhalt the CPU, it will do one instruction and then halt again. And you can see if it hit an e-break, a breakpoint instruction, by checking for that bit. So from this one register, we actually get everything we need to control the CPU. That's 50% of what we need from a single register. That's pretty cool. Now, I'm going to take a bit of an aside here, and I'm going to talk about the RISC-V instruction set. This is an example of what the instruction set looks like. If you're curious about more about the encoding for RISC-V, the URL there, rvcodec.js, is actually very good for exploring this sort of thing. But the basic tenet behind most RISC-V instructions is that there's one or two arguments called rs1 and rs2, and there's one destination register called rd. And here's an example of an instruction that takes the value in x0, which is hard-coded to 0, adds it to x1, and then stores the result in x0, which again is hard-coded as 0. So normally this wouldn't actually do anything, except when we look at how the VEX deals with its other debug register. If you write into it, what you're actually doing is sending that instruction directly into the pipeline as the CPU is paused, and it will evaluate that. And then if you read back from it, you get the destination register value from that operation. So even though we wrote into the 0 register, it's still going to generate a response that we can then read. And so from this, we can now read registers. On top of this, we can build up constants and write registers. And then we can go even further and build up, by injecting commands into the pipeline, memory addresses and then full values to be put into memory. So with these two registers, we actually get complete control over the CPU, and we have everything we need for a debugger. Now the question is, how do you connect this to the world? Well, on FOMO, we basically only had USB. And so what we did was we actually used some of the unused, reserved for vendor opcodes in the USB packet, and we ended up exposing the entire memory bus over USB. So you can send this prefix on this command and then get access to all of memory. And from here, we can access those 4 registers, and we could do everything to debug the CPU. So we actually had not only the ability to debug the CPU, but we can access memory while it was still running. And by doing that, you could do lots of really cool things, the most famous of which is RTT, which gives you a serial console over your debug infrastructure for real-time accessing without halting the CPU. That's pretty cool. So that's how we did it on FOMO and Betrusted. How do most people do it? Well, most other people use JTAG or some variation thereof, or SWD, but we'll come to that later. So JTAG, anytime you talk about JTAG, you generally get a state machine that looks like this. Hardware people love state machines because that means they can say that their hardware is in exactly this state, and there's not any sort of weird thing that it's doing at the time. But as software people, this is kind of complicated. So really the only thing you need to know about this is that there's 4 wires, TCK, TDO, TDI, and TMS. TCK being the clock, TMS being the state machine, or the state that it's in. TDO and TDI are output or input. This is from the perspective of the chip. So TDO, from our perspective as the debugger, is actually an input, and TDI is an output, just to make it a little bit weird. Data is captured on the rising edge of clock, so the entire state machine moves between states when clock goes from 0 to 1. This slide doesn't look very good on the PDF. I was supposed to talk about how we can simplify it down to 4 states, and we go between them, but here's just an example of what the clock looks like if you happen to be partial to timing diagrams. So basically the way we peek and poke is we go into the shift IR state, which is kind of difficult to see without a pointer. I guess I could use the arrow, which is very difficult to see, but I'm going to rely on human motion. This guy right here. So using a particular pattern of TMS and TCK, we get to here, then we clock in our value, and then we go 1, 1, 0 to get back here into run test idle. and then when we want to shift the actual value in, we come to here, shift DR, we put our data in here, and then we go back to run test idle. The important thing to note here is that data only takes effect when we go from shift DR into run test idle. So we can do whatever we want, but as long as we don't take this path, the machine won't actually take effect. So basically, our peek and poke becomes setting the instruction register if it's changed. If it hasn't changed, there's nothing we actually do, just leave it as it is. Then you write the data register, you go into this captured DR state, write the value in, and get the response back. One of the interesting things to note here is that it's impossible to write without reading, and you can't read without writing. So this actually has some interesting implications when it comes to the protocol, and we'll discover how some protocols handle that. So I'm just going to come up with this hypothetical JTAG device. This JTAG device doesn't exist, but in this hypothetical JTAG device, there are 2 bits in the instruction register. The important thing to note here is that instruction registers always have the same bit width for every device on the bus, but the bit width varies depending on which device you're talking to. Our device has 2 bits, which ought to be enough for anyone, really. Down here at the bottom, we have the bypass register, which is actually the only register that is defined as you must have by the JTAG standard. It's all ones. And what that does is it turns it into, well, a bypass node. It just becomes something that's hanging out on your bus that's 1 bit long. And this generally has implications for chaining devices together. Everything else on here is hypothetical, just for purposes of explanation. Up at the top, we have the ID code, which isn't defined by the JTAG standard as being at a particular address or that you must have it, but it is defined that if it does exist, it's 32 bits, and it's going to contain the JTAG vendor who made this particular part. So if you can figure out where the JTAG or the ID code register is, you're going to get 32 bits back, and that'll tell you what you're talking to. These other 2 that I put here, info and command, I just invented those names. They happen to be 20 bits and 42 bits. What are they? Well, who knows? It's really implementation defined. And really, that's all you need to know about JTAG. So now what? Well, a lot of us are engineers here, and we know what the answer to that is, right? It depends. So let's talk about ARM ADI v5/memap. This is what a lot of your ARM microcontrollers are going to use, anything that's Cortex, or I think some of the newer A series use this. So we can ask the same question we asked earlier. What do we need for a debugger? Well, let's start right in. There is this lovely table in the reference manual that I'm going to be talking about a lot, the ARM Debug Infrastructure Architecture Specification ADI v5.0 to 5.2. You can see the ID code in there at the bottom. There's the bypass register that's required. But we're interested in these 2 registers right here, DPACC and APACC. And let's look into those a little bit more. So when we talk about the JTAG message that gets sent on the wire, it's 35 bits. If you look at this table, you'll see that both DPACC and APCCC are both 35 bits, which is kind of a weird number, right? We're used to things that are 32 bits. 35 is a very, very strange number. Well, when we send messages on JTAG, we actually do the bottom line here. The first bit that we send is RNW, 1 for write, I believe, 0 for read, 2 bits of address, and 32 bits of data. And what it's going to do is it's going to send us back 3 bits of response and 32 bits of response data. I put the response here because we're actually not going to be looking at it too much. If it comes back as a 1, that means, hang on, I'm still working on it. If it comes back as 1, 0, then that means it could have succeeded, it could have failed. You're going to have to look in harder to figure out which one of those 2 it is. But I'm going to talk about the right half of this, what we send the target. those 32 bits plus 2 bits of address plus a read or write bit. For the DPACC register, this is, remember, one of the JTAG bits. So this is a JTAG register. If we set the address bit, remember it's only 2 bits of address. Address 0, it's one of those things where depending on the version of the spec you're talking to, it could be one thing, it could be something else. We're just going to ignore it completely because for the most part you can. Address 1 is this control stat, and this is how you do some very important setup for talking to the chip that of course we're going to completely ignore for purposes of time. So if you're implementing this yourself, you will need to look at the reference manual to do things like turn on the debug machinery and figure out which version you're running. But for the most part, we're just going to ignore the control and stat registers. Then we have the read buff down here at the bottom. And this is actually a really interesting register because if you read from this, it gives you zeros. Now, why would you want to do that? Well, it's because, remember, in JTAG, we can't write without reading. Anytime we send a message to the target, we have to have some operation that takes effect. And so what you do is if you say, hey, give me the read buff, then that is kind of a way of doing a no operation that will cause it to do absolutely nothing, but give you the result from the last operation you made. So this is how they work around that limitation of the JTAG spec. And then we have this select register. And this is actually, we won't be accessing the DPACC register very much, but when we do, most of the time it's going to be accessing the select register. It looks like this. There's really only 3 fields. There's DP bank cell that does some things about selecting the control stat register that some of the newer versions require for actually getting set up. We're going to ignore that. Then there is AP cell here on the far side. What this does is this actually is how the ADI v5 protocol does multi-drop. It may be that you have multiple CPU cores in here, and by setting a different AP cell, you'll talk to a different one of those cores. But then there's this AP bank cell, and I could say that that sets the access port bank, but that doesn't really tell you much, does it? So I believe that this is well described by this very clear diagram in the ARM debug infrastructure specification. So fortunately what we want is we want this section right here. This is actually the registers from the ADI v5 specification for accessing these. This is what they call a MEMAP. And we're interested in these 4 registers right here. And so what I'm going to do is I'm going to take this purple box and I'm going to turn it on its side and kind of zoom into it a little bit to get a better idea of what's going on. This is what it looks like here. So you could see the same CSW, TAR, DRW, just kind of rotate it on its side to make it easier. What this AP bank cell does is it moves the red box up and down. So it selects the bank, which one of these 4 registers we want to access. And then the 2 bits, remember from 5 minutes ago when we were talking about the actual JTAG packet, it came with 2 bits. Those are what select the X column. So an address of 0 would access CSW, an address of 3 would access DRW, or BD3, or IDR. Your choice depending on what the AP bank cell is. Now again, most of these don't really matter. This bottom row that I have highlighted right now, that is things like the IDR, and that will tell you which device you're connected to. That'll tell you you're connected to a Kinetis or an STM32. Sometimes it'll even tell you which one of those you're connected to. But for the most part, you're going to read that once when you connect, and then never again. Similarly, the base register and the base high, if it happens to be a 64-bit device, you're going to read those to get some ROM tables that will tell you more information about what the chip is, but for the most part, you'll read it once and then never again. Config register also contains things like stride when you're accessing multiple devices with auto increment. But again, it's the sort of thing you set once and never again. BD, or the banked data registers, those are for some specialized acceleration for accessing the same 4 registers over and over again. We're not going to cover those. And then you have this top row here, CSW, TAR, and DRW. And this is what we're actually interested in. By setting an address in the target address register, TAR, we have the ability to specify which address to access. And then by accessing DRW, either through a read or a write, we gain the ability to access all of memory. And in fact, not only do we access memory, but we do it while the CPU is still running. So finally, after all of this, we have the ability to peek and poke memory. Phew, that's a lot for 2 out of 8. That's a quarter of what we needed, and we spent how long on that? Fortunately, it's called a MEMAP because everything else is basically a memory access. Now that we have this primitive of being able to access memory, everything else basically falls into place as being another variant of that. So for starters, for registers, reading and writing, there's this group of registers here. And the nice thing is these addresses are fixed, and so you can just access these registers to be able to do things like halt the CPU, access various actual register values. There are these 2 registers here, DCR-SR and DCR-DR. By putting a register number like 0 for R0 in reg cell, you can say I'd like to access register 0 or register 1. And then by setting the bit in reg WNR, you can either read the value into debug temp or write the value that you've previously written from debug temp into the CPU. And so with this, we now had the ability to read and write registers. That was a lot faster than getting memory working. Just memory accesses at that point. Control isn't much more difficult. There's this register DHCSR, the debug halting control and status register. You can set the C step and C halt bits to single step and halt the CPU. Great, that's 2 more check marks. That means there's 2 more left. For that, for reset, there's this address here called a register called AIR-CR. And if you put the key of 05FA, which is required, and you set the sys reset request button register, the CPU actually resets itself. And the interesting thing is this is how operating systems work. So if you use Zephyr or NutX or one of those, they'll write this exact same register from its own CPU to cause a reset. So we're not even doing something that's debug specific here. That's pretty cool. So that's 1 more tick mark, which just leaves break, which you actually can do by setting these fields right here. When the CPU is halted, the halt bit gets set, so all you have to do is continuously read from memory to see if the halt bit is set. And if it hit a breakpoint, for example, then the breakpoint bit will also be set. So with all of that, we finally have everything we need for a debugger. We have all the little primitive bits and pieces we have for a debugger. And so just to recap everything we've talked about so far, up at the top we have JTAG with its data register and its instruction register, and then we write into the data register to access the APACC and the DPACC, which are like the ADIV5 specification. And then from there we set the bank using the DPACC register. And finally, by writing into this APACC register, we can access MEMAP, and we can get access to main memory. So that's everything we need to access an ARM CPU over JTAG. What about SWD? Well, remember this slide from, 10, 15 minutes ago now? This is what it looks like for SWD. And this didn't come out very well in the PDF, but the acknowledge bits, there's 3 acknowledge bits in the SWD packet that is almost the same as the 3 acknowledge bits from JTAG. We have 2 bits of address, the exact same 2 bits of address from JTAG. Instead, we have the same 1-bit read and write that goes before the address bit. But now instead of accessing a different JTAG address, we just have this 1 bit towards the beginning of the frame that sets the AP or the DP. So what they've done is they've taken everything you use as JTAG and just put it in one message that you send the target. Everything else just gets stuck in the data field, but everything else is actually identical between JTAG and SWD. The only difference is the framing that goes on beforehand, and the fact that it's on 2 wires rather than the 4 wires of JTAG. So because there's a lot less overhead, this can usually be faster. They also threw a parity bit in there just for good measure, so it's also more reliable than JTAG. And of course, reading is the exact same, except the read and write bit is now 1 instead of 0. So what about programming Flash? I did mention in the discussion that we talk about programming Flash. Well, that is basically writing to memory. And so what you can do is you can actually write the driver for the Flash in your debug software. And this you can get pretty far with this. This is what the Blackmagic probe does. This is what a lot of the Seger software does, is they get one of every kind of chip available and write a Flash driver for it. So they can make Flash drivers that are very tuned and can be very fast for a wide variety of targets. Now, this is a very, very manual and time-intensive process. So what ARM did is they came up with what's called a Flash algorithm that is something that your chip vendor might provide you that is a big XML file that contains a bunch of entry points, and the idea is you load this into code and you jump to it with pointers set the correct place, and in theory, it will just flash the target for you. This can actually work reasonably well. This is what probe RS does, and this is what PyOCD does. But it does mean that you tend to have slightly worse performance, and it can be very difficult to customize this for different targets. So both options are available. You can actually do both in the same project. I believe probe RS at least supports custom Flash algorithms. But by and large, this is how you would actually program Flash. Okay, what about RISC-V? Well, RISC-V, they have a debug standard that you can get the PDF of. It's published online, and for the most part, it's a pretty good standard, but there's a few places where it's actually 3 different specifications in a trench coat. If you open the standard, there's this table here that looks an awful lot like the one in ARM, except some of the addresses are in different places. You could see their ID code is actually address 1 now instead of towards the end like ARM is. But we're mostly interested in these 2 addresses right here, DTM, CS, and DMI. So that's debug, control, and status, and the debug module interface access. So for DTM CS, it looks like this. And this is the sort of register, again, we're going to read more or less exactly once and then never again. It contains one field that's the number of times you need to let it idle. For the most part, this will be 0. It contains the size of the address bits that we'll see in the next slide, and it contains the version of the debug standard. So for the most part, you're going to be reading this and making sure that it's what you think it is, and then never read it again. For the most part, you're going to be reading address 11, JTAG address 11. And to start with, for the opcode, when you send a packet, if you set the opcode to be 0, it does absolutely nothing. So this is how the RISC-V standard deals with the JTAG. You can't read without writing, you can't write without reading. If you send it a command and the opcode is 0, it does nothing. Conversely, if you set it to 1 or 2, it'll actually perform that operation by reading or writing to the debug module interface. And of course, it will respond to you at the exact same time. 0 means success, 2 means failed, 3 means, hey, I'm still working on it. Then 32 bits of read and write, and then 7 or some odd, however many bits it requested, it said you can have in address 0 or 10 of actual data. And there are, well, there are 511 different possible commands, most of which are fortunately not required or even implemented on most targets. So we can ask the same question as earlier, what do we need for a debugger? For starters, there's this register, address number 10. This is, remember, within the DMI address space. We're not in JTAG land anymore. We're now within the RISC-V debug module interface. There is this address 10 that contains the bits that I've highlighted here. And this lets you halt and resume the core, reset the core, which they call a hardware thread, and it lets you undo that reset. So here, very quickly, we actually have 2 out of 8 things we need for a debugger. That's a pretty good start. What about accessing registers? Well, there's this thing called Abstract Access Register, AAR, and what this is you send command 17 with the first couple of bits as 0. And what this says is I'm going to access a register. You set the address size to 3. You set the transfer bit to 1. Very important that the transfer bit is 1, because otherwise it won't actually do anything, which is kind of a weird thing that we'll come back to in a bit. Set 1 for write, 0 for read, and you put the register number in for regno. Makes sense, except that you have to OR your register with 1000, aux 1000, which is kind of weird, okay? So you want to access register R1. You have to specify the register as aux 1001. Kind of weird. We'll come back as to why that is in a bit. But the data will pop out at data 0, which is at address 4. Okay, great. So now we have the ability to read and write registers. Let's look at memory. Okay. Well, this is where things get a bit weird, because there's this line in the manual that says, in order to be compatible with this specification, an implementation must implement at least one of program buffer, system bus access, or abstract access memory, which means now we have a choose your own adventure. So as the person implementing the CPU, you get to pick which one of these you want to implement. But us, as the people implementing a debugger, we have to implement all 3 if we want to be able to work with every device. So the designer gets to choose, the debug author has to do all of them. So let's go through these one by one. Let's start with the program buffer. So the program buffer is basically what we did with the VEX RISC-V. What they do is they give you anywhere between, well, actually 0, if it doesn't support it, 1 and 16 32-bit values where you can load a very small RISC-V program and tell it to go. Some target cores require you to end with an e-break instruction. Some of them don't. If you only have one program buffer, obviously it doesn't make sense to require an e-break instruction there. But for the most part, you have to put an e-break at the end of your program to tell it that, hey, I'm done with this. It's a lot of unspecified values here. For example, it's not specified if the program actually gets put in memory. It might just be in a special value that gets stuffed directly into the pipe. This is all unspecified, and the designer can do whatever they want. You actually run the program by using this same abstract access register, but you set postexec to 1, which is after we write this register, execute the program in the program buffer. And so this is why there's this transfer bit, because if you set it to 0, then it will just execute the program without actually transferring any values. Okay, so that's program buffer. What about abstract access memory? Well, this is using the exact same command that we use for abstract access register, which is why it has a very similar name. But now the command type is 2. It means access memory instead of registers. And now, because the address doesn't fit in the actual command register anymore, now we put it in the data 1 register. The data still appears on data 0, so this behaves very much like the access register, except now it behaves on memory. And interestingly enough, one of the reasons why they call this abstract access is because a lot of times it's implemented in microcode. This is an example from the Hazard 3 core that's in the new RP2350, which has an open source core, by the way. And you can see here they've actually encoded 32-bit instructions that when you call abstract access memory, it's going to actually execute these instructions by putting them directly into the pipeline. So it's pretty cool that you can actually see what's going on the inside of these open source cores. So the last of our 3 options is the system bus access. And this is actually the coolest of the 3. Because this lets you access main memory while the CPU is still running. It's very similar to the other 2 in that you would have SB data 0, which is where the data gets read to or written from. You have the address at another address, SB address 0. And you could set all sorts of things like when you write to the address, read from that value and stuff it in the data register. Otherwise, if you write to the data register, that gets sent immediately to the address that is currently in address. So by doing this, you can actually make a very efficient way to read and write memory while the CPU is still running. And so this is how you'd, for example, get RTT working on a RISC-V core. But again, remember, this is optional, so you kind of have to discover if your core even supports this. I'm going to put the little star here rather than on the next page with our debug access list, because it's optional, and so it's not required, unlike with ARM. But it's nice to know that this is possible on RISC-V. So with that, we have 6 out of 8 of the things we need for a debugger. All we need is the ability to single step and break in, or detect if we've hit a breakpoint. And so for that, we can look at this debug and control and status register. So there's a bit there called step, and if you set that to 1, it will single step. That's exactly what we're looking for. There's a cause register here that will tell you why the system halted. 3 is we've requested it to halt. 4 is it was single stepping. 1 is it hit an e-brake. Okay, that's pretty cool. But if you look at the address, it's 7B0, which is weirdly far away from all the registers we've looked at so far. The command register was 17. The data register was 4. 7B0 is pretty far away from that. Why is that? It's because it's in a completely different address space. Up until now, we've been talking about DMI, the Debug Management Interface address space. This is what's known as a CSR, a Control and Status Register, and it's a feature of RISC-V where it's this completely separate address space that is normally used for things like, are interrupts enabled? How many cycles have been executed? Where are we going to vector when we hit a trap instruction, for example, or a interrupt of some sort? Are we in user mode? And so this is a completely separate address space that we need to be able to access somehow. And we do that by, normally what we would do is we'd set the, earlier we set the, when we were accessing registers, we had to OR them with 1000. If you don't OR them with 1000, if you just put a number in there, by default you're accessing the CSR address space. So earlier we were wanting to access 7B0. If we just try to do accessing CSRs for 7B0, what we would do is we would actually be accessing that by accessing it like a regular register. Except it turns out that actually supporting this is also completely optional. So it may be that you can't access the CSRs this way, and you just have to implement them using program buffer, because there's another line in the reference manual that says in order to be compatible with this implementation. Earlier we were talking about point 2. Point 3 says, yeah, you have to either implement program buffer or complete access. And it turns out the Hazard 3 core does not implement complete access. So if you want to access CSRs on the RP2350 Hazard 3 core, you actually need to use program buffer anyway. So with that, we have everything we need for a debugger, and we have everything we need for a debugger with the RISC-V specification. That's pretty cool. I do want to take a brief aside. We have another few minutes here, and we'll first off go over a summary. 4 different address spaces within RISC-V. There's JTAG with the address 10 for the CSR, address 11 for the DMI. There's the actual DMI address space, which is everything we were talking about earlier. There is, of course, RAM, which is mostly what we're interested in accessing. And then there's the CSRs, which we're going to need to access for things like single stepping and halting the CPU. There are 3 different ways to access memory: program buffer, abstract access memory, or system bus access. 2 different ways to access CSRs: program buffer, abstract access register. Fortunately, there's only one way to access the general purpose registers with abstract access register. So this is the summary of RISC-V. I do want to take a brief aside now and talk about the RP2350, which does something that's actually really cool. RISC-V over SWD. Normally you think about SWD as being exclusively ARM, but the RISC-V Foundation with their newest chip actually did something really cool with the debug situation. Up until now, we've been talking about ADI version 5, The RP2350 is a little bit annoying because it's a newer version of the spec, but the biggest thing we need to worry about is that this register with the AP cell, the AP bank cell, and the DP bank cell, one of the things that ARM did in the newer version is they just combined it all into one. There's a single field there called address. And so now rather than setting a different application or access port in a different bank, it's all just in single address space. And if you open the RISC-V manual, there's this really nice picture here of all the different addresses on that debug port. And you can see there at address 0A000, what they did, the mad people, is they actually put a memap there that instead of accessing a memory space, a RAM space, it's actually just the DMI. So take your DMI value, multiply it by 4 because they're 32-bit values, and now you're accessing the debug module interface over SWD using this memap. And everything else here just automatically works. So all you have to do is change your interface, and the entire set of machinery that goes on behind that just works. So to recap what we talked about over the last 45 minutes, we started by talking a little bit about the JTAG basics, and we took a brief peek at what SWD works. We covered ADI5 with the memap, and then we actually took a detour for RISC-V and talked about how they do it over JTAG. It mentioned the RP2350 and how that works over SWD. I want to say that this isn't everything. There's always a lot more to learn. We didn't cover anything like hardware breakpoints, which, at least to the memap situation, are just more memory addresses, particularly with the flash, patch, and breakpoint register. We haven't talked about multi-drop SWD, which is how the older RP2030 worked. We didn't talk about protocol initiation, other than to say we're not going to talk about protocol initiation. Very important if you want to come up with your own debugger, but mostly it involves setting things up and letting it run. We also didn't talk about protocol recovery, which is something that only a few debug protocols work on. If you're working on your own operating system or whatever, you're going to be doing things like changing the PLL, and maybe you mess up and now it's in a locked state. So you're going to have to recover that target and get back into a known working state. That's a very complicated series of things because, of course, if you're a hardware person, you have that nice state machine with 16 states, but as we all know from software people, things tend to get into very weird states, and getting them out can sometimes be a challenge. We also didn't talk about any other debug protocols. There's JTAG PDI, which is how you do JTAG to AVR chips. There's WCH Link, which is how you do a one-wire debug to some of the very cheap CH32, the very cheap 20-cent microcontrollers. BDM is the background debug mode that NXP has for their little 8-bit microcontrollers. There's lots more available out there. But anytime you encounter a new protocol, just ask yourself if you have those 8 things that we talked about earlier, to let you know if it's even feasible to get debugging set up. And then there's tracing, which is a whole separate series of talks, and it's something that the open source world is only just now starting to learn about and develop software and hardware tooling for. I hope that this talk has at least reduced some of the mystery as to what goes on over these little wires to help getting your debug situation under control and understand your tooling and your setup a little bit more. And I hope you understand a little bit more about what's going on the wire. And with that, thank you everyone for listening.